This is Maes Gilbryn, firstborn of the 13 Burn, lucky Maes of the scattered archipelago, and the witch of Keelholm Sounding. This is you, brought to the bone chips of the dead for daring to say that mangoes taste like toothpaste. Perhaps Maes rubs her luck on you today because you find yourself as one of the crew on her very own ship, Tide Child. A lovely day indeed. Untruss my bows, let us fight the sea monsters of the North Storm. Fear not, though, because you've attended Mr. Moose's one and only SBH4U course, so you've got some tricks up your sleeve. First of all, what is a gallowbow? In R.J. Barker's novel, The Bone Ships, the gallowbow is a massive bow that is used on bone ships for battle. Almost twice the size of a grown man, the bows line the main deck's borders. The gallowbow is stored tied to the legs attached to a gimbal, which is a little pivoting stand to turn and rotate the contraption. It has 2 arms, as well as a cord that threads around each arm and is cinched tight so that the bow quivers with tension, much like a normal bow and arrow. The first 3 instructions before launching the bolt is to knot, lift, and string the bow. We are finally ready to release the bolt. This consists of 4 steps, the first one being spin. This step means that the handles on the spinner of the gallowbow are wound, the mechanism on the bow linked to the cord pulling the center of the string back. The draw weight, which is the applied force to pull the string back, is represented by this FA vector here, while Fs, the elastic force, is denoted at the arms of the bow, as a result of the stiffness of the arms, which has to do with the material of the bow, as well as the X displacement of the string as it pulls on the ends. It's important to note that the gallowbow mechanism is designed to pull the cord at its half length. This is to achieve the highest X value. You can see this in these 2 adjacent diagrams. The top evidently has a lower X value than the bottom, since there is a less cord between the arm and the pinched part of the cord. Another huge distinction is that we need to know where the EPE, the elastic potential energy, is truly coming from. On an average recurve bow and arrow, the string tension only changes by about 250 newtons as you draw back, but the string only contracts around 0.1 to 0.2% of its actual length, which is where the EPE is supposed to be coming from. Therefore, the string does not contribute all that much to EPE. Rather, the pull of the string on the bow arms curve the arms back, deforming the bow's shape into one that holds a strong amount of EPE that can be released and converted to KE, kinetic energy, as it once again reforms into its equilibrium state. The second step is load, which has to do with loading the bolt into the gallowbow. 2 things need to be discussed here. The first one is that lighter arrows will move faster. Second, a lighter bow string will increase the arrow speed. Both of these concepts follow the basic formula of kinetic energy. EK is equal to half mv squared. Keep in mind that EK in the bolt starts at 0, but will increase from the release of the EPE in the bow arms. We can consider for this step that EPE is a set value and none will be lost to other energy forms. For this reason, the formula clearly shows us that a decrease in M will result in a slight increase in V as the 2 values are inversely proportional to one another. This is why lighter arrows can travel fast. Now, for the second part about the lighter bow string increasing the arrow speed, this is where an amendment to my previous statement is needed. EPE is actually not completely converted to KE as it transfers into the arrow, or the bolt. Because the energy travels through the bow and cord, they also experience kinetic energy in the form of moving back into their original shape and vibrating slightly. This will be explained in a future panel, no worries. We can prove this, though, by considering the moment the trigger cord to loose the arrow is released. We can say that the electric potential energy is equal to the kinetic energy in the arrow plus the kinetic energy in the bow. We can then factor out the 1/2 as well as the velocity, because as the arrow is moving forward still connected to the bow, they all move at the same velocity. Now you can rearrange for velocity, and you find that V is equal to 2 EPE divided by the sum of the mass of the arrow and the mass of the bow. As you can see from this rearranged equation, V is dependent upon the mass of the bow, in a way that if MV were to increase, the velocity would decrease, and the opposite is true as well. Division by a greater value yields a smaller quotient. The third step is to aim, and this is where we can get into some interesting mathematics. To start, though, we need to know that the gallowbows are not angled on the gimbal and can be raised or lowered due to its weight. For this reason, the degree of motion in the y component of force is very limited. So therefore, projectile motion is without a Vy component. The force of gravity will only let it move downwards after the bolt is launched. Dx is key to consider when making sure you hit the opposite ship where you must, depending on their height. Onward, courser, I haven't the scarce burning eye to wait for your blithering Newtonian chicken scratch. Provide me accuracy within 3 turns of the glass. Let's find a strategy to aim aboard Tide Child. Let's assume we know the velocity at which the bolt will shoot. I mean, how could you be a deck child if you didn't know? And say that Vx is equal to 125 meters per second. We shall make the xy separate t-chart to formulate a method. There is no ax, and ay is simply the acceleration due to gravity. Vx is our trusty 125 meters per second, and Vy is 0 meters per second. The x component experiences a constant velocity, so we can use the basic velocity formula in all regards. Working on the right, we will use a Fab 5 equation, since acceleration is not zero, and we see that both formulas share a delta t. Rearranging for t allows us to substitute delta dx over vx into the delta dy equation. As you can see, if you know delta x, the distance between your ship and an enemy, you can expect what height of their vessel you will hit. As seen in this diagram, you can adjust your delta dx and properly plan when the battle should begin, based on distance. How do we find dx, you ask? How childish, courser. Use your eyes and thumb and estimate the distances. That can be explained another day. The final step is to loose. The trigger cord is yanked back and the bolt is released from the bow shaft. The elastic potential energy of the bow arms transfers to the bolt, sending it soaring away. Now, as we mentioned before, not all EPE is given to the bolt. Some of it goes to the arms and the string of the bow as kinetic energy. There are also other ways as well. First, de-knocking energy. As the bolt accelerates out of the bow shaft, the shaft of the bolt naturally rubs against the material of the bow shaft, causing negative work of friction to occur. The de-acceleration exists, and some energy is definitely lost to sound and thermal energy. Still, Maes Gallowbows are likely lined with verisk, which can be a material as smooth as glass if handled properly. Next, recoil energy, which is as a result of momentum. The conservation of momentum requires that the momentum in the system you begin with must be what you end up with. To start, both the bow and the bolt are at rest, so despite their masses, their momentums are zero, and therefore the total momentum in the system we will work with will always be zero. That means that after the launch, the bow and the arrow move in opposite directions. Once the bolt soars away in one direction, we will assign right as positive for this demonstration. To maintain the zero momentum, the bow has to be moving in the opposite way to accommodate for the opposite sign of the velocity. However, the mass of the bow will be significantly larger than that of the bolt, so to make sure the two momentums add to zero, the velocity of the bow will have to be a small value significantly as well. A change in velocity requires an acceleration, which requires an F net in the direction of motion of the bow. That is the recoil energy used from EPE. It should be mentioned that the recoil energy on a normal recurve bow is about 0.18 joules, which is insignificant in proportion to the total EPE that is available in the normal bow. So there isn't too much concern there either, in proportion to, let's say, a Gallowbow either. As the bolt soars, the drag force will also do negative work, which is proportional to the cross-sectional area of the shaft of the bolt and to the air density. The good thing is that as the bolt descends, the gravitational potential energy converts to kinetic energy as well, which will add to the power of the bolt at collision. So overall, you start with elastic potential energy and gravitational potential energy, since you are much higher than even sea level. Then the elastic potential energy is converted to kinetic energy of the bolt and bow, as well as the negative work done as the bolt is de-knocked, if you will, and let loose. As the bolt is soaring in the air, the two main energies there are its kinetic energy and the gravitational potential energy, then the negative work done by drag, and lastly, its lost energy forms, which are always present in this case. As time goes on, the bolt curves downward, because e.g., gravitational potential energy is converted into kinetic energy until eventually all you are left with is the arrow or the bolt's kinetic energy, right before collision. And once the bolt hits the opposing enemy ship or the elusive sea monster, you're in for a heavy-duty, completely inelastic collision. As for ships, the bolts break through the deck or hull often, and in the underdecks they hit and stick. So even though the overall force of the hit is high, the time that it is continuously met with bone and infrastructure is enough to allow for a greater decrease and eventual stop of the velocity of the bolt, eventually rendering it useless. Congratulations, you successfully managed to carry out the shipwife's order. Maybe the fleet isn't so hard after all. Good, now again.